In this session, we are going to start the interpretation of proton NMR spectra. So when you go for taking an NMR spectrum using NMR instrument, you are getting this FID file from the NMR instrument. Now you convert this FID file to frequency domain spectrum using computational method, but you stuck here because it's not telling anything about the structure of organic molecules. So for finding the structure of organic molecules from this frequency domain spectrum, you have to go through these all steps. That is, you have to find number of signals, you have to find the position of signals, you have to find area under the peak, means integration, and you have to look for splitting of signals. So in coming lectures we will go through all these steps one by one to interpret the spectra to find the structure of organic molecules. So let's start with number of signals. So the number of signals in a proton NMR spectrum shows how many types of proton are present in a molecule. Or protons with same chemical environment resonate at same radio frequency, whereas proton with a different chemical environment resonate at different radio frequency. So the proton with same chemical environment are said to be chemically equivalent protons, and they always give one signal. So let's see some example. So this is dimethyl ether. So you can see all 6 protons are equivalent. So we are getting one signal for all 6 protons. In this molecule, which is a dichloroethane, we have 2 types of proton because the environment of CH3 protons is different than CH2 proton. So CH2 proton will appear at different place and CH3 proton will appear at different place due to different chemical environment. So overall we will get 2 NMR signal for this molecule. In this molecule there are 3 types of proton. Here 2 types of CH3 proton and one is CH2 proton. So finally we will get 3 NMR signal for this molecule. Benzene, there is no substituent on benzene, so all proton of benzene are equivalent, means they have same chemical environment, so we will get only one signal for benzene. Same for cyclohexane, all 12 protons are chemically equivalent because there is no substituent, so it will give only one NMR signal. So chemically equivalent protons give one signal and chemically not equivalent protons give 2 or more signals. Now types of proton. So protons can be 4 types: homotopic protons, anisotropic proton, diisotropic proton, and heterotopic protons. So homotopic or anisotropic proton are chemically equivalent protons, while diisotropic and heterotopic protons are non-equivalent protons. Let's see what are homotopic protons. Homotopic means identical. So for example, all the protons in ethane are homotopic because the rotation about this carbon-carbon single bond is so fast that NMR cannot distinguish them. So all the protons appear in the same chemical environment and they give only one signal in NMR spectrum. So all the 6 hydrogen are in the same environment surrounded by the same type of atoms at same distance and angle, so they are chemically equivalent, so that's why they are giving only one signal. Now how we can find that 2 protons are homotopic in a molecule? For this we have to use a replacement method. The simple method to decide the chemical equivalence of 2 or more protons is to replace each proton in turn by some other atom. For example, X. If replacing 2 protons with a different group give the same compound, the proton are called homotopic protons. So in this example, if we replace first HA protons with X, we are getting this molecule. In second, we replace HB with X, we are getting this molecule. But now if we will look, these 2 molecules are same after replacing either HA or HB with a different group X. So this shows that this HA and HB are homotopic proton. So this is another example, as we have seen in last slide also, that all protons in ethane are equivalent. So let's see the example of HA and HB by replacing them with X. So first when we replace HB with X, we will get this molecule. When we replace HA with X, we are getting this molecule. Now if we rotate them 120 degree around CC single bond, we are getting same molecule, means these two are the identical molecules. So that's why HA and HB are homotopic protons. So they will give one signal. Now what are anisotropic proton? If replacing two proton with a different group X gives a pair of anisomers, the protons are called anisotropic. Let's say in these two molecules. So when we replace this HA with X, we are getting this molecule. So this molecule now become a chiral, because all four groups connected to this carbon are different. Now replacement of HB with X, again giving this chiral molecule. So now these two molecules are an anisomer of each other. So means these two proton HA and HB are anisotropic proton. However, anisotropic proton are chemically equivalent and they also give one signal in NMR spectrum. Diisotropic protons, if molecule already has a chiral center, then replacing two protons with a different group will give a pair of diisomers, and those protons are called diisotropic protons. So let's see in these two examples. So these molecules already have a chiral center at this carbon, because all group are different at this carbon. Now when we replace HA with X, we are getting this molecule which has a new chiral center. Again replacing of HB giving this molecule which also have a new chiral center. So these two molecules having two chiral center by replacing HA or HB with X. So these HA and HB are diisotropic protons. So all diisotropic protons are not chemically equivalent and they give two signals in NMR spectrum. This is another example of geometrical isomers. So this HA and HB replacement with X give two different geometrical isomers. So means HA and HB are diisotropic proton and they will give two signal in NMR spectrum. So now homotopic and anisotropic protons are chemically equivalent. They give one signal, while diisotropic proton are not chemically equivalent. They are giving different signals. But the replacement method is overwhelming and time consuming. So how we can find that two protons are homotopic, anisotropic and diisotropic using some other method. So to solve this problem, we have to find a symmetry which is exchanging those protons. So this symmetry can be plane of symmetry or axis of symmetry. So for example, the following molecules have lot of hydrogens, but because they are symmetrical and hydrogens are in identical environment, because they have same connectivity and they have same neighbors and therefore resonate at the same frequency. If you look in this molecule, this has plane of symmetry and axis of symmetry. So this CH3 is equivalent to this CH3. So both 6 proton will appear at the same place. So finally we will get only one signal. In this molecule, there is a plane of symmetry as well as axis of symmetry. This CH3 proton is exchangeable by plane of symmetry or axis of symmetry by this CH3 proton. So they will appear at same place, means they will give one signal. So in this molecule we will get one signal for 6 proton and one signal for these 2 proton. So finally we will get 2 signal for this molecule. In this molecule, this has again plane of symmetry as well as axis of symmetry. So these CH3 group are exchangeable with this CH3, means these 6 proton give one signal and these 2 proton give their one signal. So finally we will get total 2 signal in this molecule. And in this benzene, substitute benzene example, we can see that this has a plane of symmetry and axis of symmetry perpendicular to the plane. So these B protons, like this proton and this proton, are exchangeable by this plane of symmetry or axis of symmetry. This proton and this proton are exchangeable, and so these in this molecule we will get total 4 signal. One signal for B proton, one signal for C proton, one signal for D proton, and one signal for this methyl protons. So how we will remember that? We have to remember this flow chart. If there is axis of symmetry, then between two protons, then those protons are homotopic proton. If there is no axis of symmetry, then we have to look for plane of symmetry. If there is a plane of symmetry, those two protons are anisotropic proton. And we have to remember anisotropic proton and homotopic protons are chemically equivalent and they give signal at same place. Now, if there is no symmetry between two protons or two groups, those are chemically non-equivalent protons and will give different signals. So same thing is written here. If the two protons are exchangeable by a symmetry axis or can be reflected through a plane of symmetry, if they have either of these, they are equivalent and will give one signal. To determine the relationship of these protons, remember that symmetry axis means homotopic, and if there is no axis but there is a plane of symmetry, then the protons are anisotropic. If the protons are not related by these symmetry elements, they are not equivalent and will give two or more NMR signals. Now we will discuss some examples. So in this example, which is a cyclopropane, the two protons A and B, this is a methyl proton and these are the two protons are exchangeable by a plane of symmetry. Finally, these two protons will give same signal and these two methyl will give same signal. In the next example, if we see here a plane of symmetry with the plane of paper, and by this plane of symmetry these two protons are exchangeable. We will get three signals in this molecule, one for this methyl, other for this methyl, because these two methyl have different chemical environment due to this oxygen, and these two protons are exchangeable by the plane of symmetry through the plane of the paper. So they will be anisotropic protons and they will give same signal. Now in these two molecules, these two protons are anisotropic protons because they are exchangeable by C2 symmetry. Because this molecule has two chiral center, but when you rotate it according to this axis, this proton rotation will give you same molecule. So means these are the interexchangeable protons through this axis of symmetry. So again they will give the same signal. In this molecule, these two protons are exchangeable through again C2 axis of symmetry, and you will get total three signal in this molecule, one signal for this proton and one signal for B proton and one signal for these two protons. So finally this molecule total has 8 protons, but it will give only 3 signal due to this C2 axis of symmetry. Now these are the example of the isotropic proton. These all molecules already have one chiral center like this, and if we see exchange this proton with a different group, we will get another chiral center. So means these two protons are isotropic protons, and as we know the isotropic protons give different signal in NMR. So total these molecules have 9 protons, but we will observe only 7 signal. In this we have 9 number of total protons and getting 5 signal in NMR spectrum. However, these two protons are isotropic protons and they will give different signal in NMR. For this molecule, which we already have discussed, we discussed about this set of protons, means B and A, but we didn't discuss anything about these two protons. So total these molecules have 10 protons. These two protons are anisotropic, these two protons are anisotropic, so they will give same signal. But these two protons are isotropic protons and they will give different signal. So finally in this molecule we will get total 4 signal. So if a molecule has chiral center, then 2 protons or any other carbon in the same molecules will be isotropic. So we have to remember this condition. Now this is the last type of proton, heterotropic protons. So what if there is no plane or no axis of symmetry, reflect 2 protons and they are not stereochemically related? So for example, replacing 2 protons with another group in this molecule give 2 constitutional isomer. However, they are not chemically equivalent protons, but since they are the part of the constitutional isomers, they are just giving constitutional isomers, so they are known as heterotropic protons. And heterotropic protons give different NMR signal since they have different chemical environment. So finally we can summarize this. So homotopic and anisotropic proton are chemically equivalent and give one signal, Locate them with a symmetry axis or plane of symmetry. Now diisotopic and heterotopic protons are chemically non-equivalent and give two signals, and none of these are detectable by symmetry elements. If in doubt what relationship they represent, do the sweeping test. So in this molecule we can see these CH3 protons are different, these CH2 protons have different chemical environment, and these 3 protons have different chemical environment. So finally we will get 3 signal for this molecule. So number of peaks in NMR spectra tells about the types of proton available in the molecule. So thank you very much.